and single camera is mounted in 9-hand configuration directly in the center of the base of the gripper. Such gripper is made up of 2 brushed DC motors, with a metal gearbox and an integrated quadrature encoder. Through a rack and pinion mechanism, the motion of these motors allows the closure of the gripper fingers. The gripper is in turn mounted on a robot manipulator standing on a sliding track. The robot control unit is in charge of the compensation of the robot dynamics. An external PC with the Ubuntu OS and a patched RTAI real-time kernel generates the references for the robot each 2 milliseconds. A second PC with Windows OS is in charge of the visual elaboration process and communicates with the first one through an UDP protocol. A high-priority multi-thread programming has been employed to improve the stability of the elaboration time and synchronize the visual measurements with the robot motion. In order to provide a ground truth for the proposed estimation algorithm, an OptiTrack motion capture system composed of 10 cameras has been employed to track the ball during its motion. The portion of the camera image employed for the ball detection is limited to 368 by 512 pixels of size. The range of radius of interest for the first detection is between 10 and 14 pixels, which corresponds to a distance of the ball from the camera in the range of 5-6 meters. The ROA window is dynamically placed and sized with respect to the current radius of the detected ball. At the first detection, its dimension is set to 38 by 38 pixels. With this configuration parameters, the acquisition frame rate is speeded up to 140 frames per second. The thrown ball has a diameter of 8.5 centimeters and a weight of about 32 grams. 6 soft reflecting markers are attached to the ball in order to make the OptiTrack system able to observe it. By using the OptiTrack system, it has been possible to measure the rebound of the chosen ball on the ground. Hence, a calibration procedure has been adopted to tune the parameters in the rebound model. The intrinsic redundancy of the chosen robotic platform has been exploited to avoid joint limits, kinematic singularities, and to reduce the movements of the sliding track since its dynamics is considerably slower than those of the other joints. The initial baseline has a planned length of 50 centimeters that should be performed by the camera in 500 milliseconds. Latency periods and delays between the robot control PC, the robot control unit, and the visual elaboration PC have been estimated so as to synchronize at the best the direct kinematic measurements of the robot with the visual data.